When we look up at the nighttime sky above us, it is light that we see. It is light, set off from the darkness by being so profoundly set within it, that draws our gaze upwards and invites us into the cosmos. It has always been thus. All faith and wisdom traditions draw upon the metaphor of light for knowledge, wisdom, and revelation. We say that someone who has awoken to a new reality or new way of understanding an old reality has become enlightened. New knowledge is said to be illuminating. Yet in science, with respect to that physical phenomenon of light, this is only metaphorically true. For most of the human experience, the nature of light has been shrouded in ignorance, even as its behavior was becoming better known. Yet, as the scientific revolution came about, that all started to change. The speculations of the natural philosophers gave way to the observations of the new experimental philosophy and those who practiced it, and soon light began to give up a few of its secrets. But it only did so grudgingly. Throughout the 17th and 18th centuries, only a little was known about what it was, even as it was more aggressively gathered by the instruments developed at the beginning of the Enlightenment. As telescopes and microscopes collected light in ever-increasing quantities to peer further into their respective domains with greater clarity and precision, there was an explosion of knowledge about the realms they explored and an accompanying illumination of the objects that occupied both the very large and very small spaces of the natural world. And yet, the physical understanding of that which revealed to us these new worlds was still very lacking. At the beginning of the 19th century, though, all of that would begin to change. Even as the French Revolution and the wars of Napoleon brought the Enlightenment to a close, there were other revolutions taking place. Alongside the emergence of chemistry as a discipline founded on a new theory of matter, was finally an unfolding understanding of what light was and how it interacted with that matter. As a part of this was the surprising discovery that light could do more than just travel through space from place to place, but that it could also carry with it information about the thing that emitted it. This fact would bring about a new field of study that examined the physical nature of the objects in the vast expanse of the space beyond our solar system: astrophysics. In the rainbows of light first produced by Newton's prism and then extended upon, scientists would find a treasure trove of information that would unlock the secrets of the stars. In this episode of the Scientific Odyssey, we set out to understand how those developments occurred and what impact they had on humanity's understanding of the cosmos. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 32, Light and Spectra. As I researched the foundations of spectroscopic analysis, there was a quote from the philosopher Auguste Comte that very nearly every author just loves to cite. In his work, Cours de philosophie positive, written in 1835, Comte opined regarding the sorts of knowledge that could be obtained about the stars. He wrote, quote, "We understand the possibility of determining their shapes, their distances, their sizes, and their movement, whereas we would never know how to study by any means their chemical composition or their mineralogical structure, and even more so the nature of any organized beings that might live on their surface. In a word, our positive knowledge with respect to the stars is necessarily limited solely to geometric and mechanical phenomena, without being able to encompass at all those other lines of physical, chemical, physiological, and even sociological research which comprise the study of all of the accessible beings by all of our diverse methods of observation. I persist in the opinion that every notion of the true mean temperatures of the stars will necessarily be concealed from us." End quote. Now, aside from the fascinating assumption that stars might be populated by quote-unquote accessible beings, Comte's words almost sound a bit like something to which a modern scientist might respond, "Can't measure temperature or determine chemical composition, you say? Challenge accepted." Now, to be fair to Comte, his work was actually an important piece of discussion about the proper practice of science and the nature of scientific knowledge, in that he embraced a position known as positivism, which held that all reliable scientific knowledge should be derived from direct, simple observation. While now understood to be a somewhat simplistic approach in this way, positivism encapsulates that most scientific of ideas, that knowledge should be based on direct observation or experimentation, and it would serve as a precursor to the instrumentalist positions of men like Mach and Dewey at the beginning of the 20th century. Nevertheless, this episode is the story of proving Comte wrong in what I view as one of the greatest triumphs of the human intellect. What I would like to discuss is how over the course of about 2 centuries, humanity managed to crack the code and open the information stored in light. It is, for me, a tale of incredible ingenuity and creativity that led to a revolution in nearly every field of scientific inquiry, though most notably in physics, astronomy, and, as we have discussed in our series on the history of the atom, chemistry. So, when we talk about light, the story, of course, always goes back to Isaac Newton and his observations of solar spectra in 1666, 1667 or so. And then those, of course, were published in the Philosophical Transactions of the Royal Society in 1672. While there had certainly been others who had previously observed the phenomenon and even made a few preliminary investigations, it was Newton's particular arrangement that made careful study of the spectrum produced by passing light from the sun through a high-quality prism possible. As we have previously discussed, it was his ability to both split the light into the familiar rainbow of colors and then show that that rainbow could be recombined to produce white light, and that the individual colors could not be further subdivided, that proved and provided the necessary evidence that showed that the spectrum was contained within the light beam itself, rather than being imparted by the prism as had been previously thought. Unfortunately, as we mentioned in those episodes on Newton, his conclusion that the differing indices of refraction, or put another way, the amount light will be bent passing through a piece of curved glass, were both color dependent and uncorrectable, led him to the conclusion that chromatic aberration was unavoidable in refracting telescopes. This meant that spectra became a problem to be solved rather than a phenomenon to be more closely studied. Had the opening through which he passed the light of the sun, something often referred to as the aperture, been smaller, he might have noticed the seemingly continuous spectrum of the sun held within it a surprise. A little-known fact about Newton's spectral investigations is that he actually used a lens to also collect the light of Venus, and by placing a prism just before that lens's focal point, he was able to produce and observe the spectrum of the light reflected from the planet. Here again, he observed a continuous spectrum of color, writing that it was, quote, drawn out into a long and splendid line, end quote. The ensuing controversy regarding light with both Hooke and Huygens would delay the full publication of Newton's ideas until 1704, and it would also embroil the entire subject in enough controversy that light and spectroscopy was neglected for nearly a century. However, at the turn of the 18th century, there was ushered in a number of developments that would ultimately prove key to the reinvigoration of that investigation and, in time, the understanding of light. Let's take a brief look at each of these. The first was William Herschel's observation of the heating of a thermometer caused by the different colors of the solar spectrum gathered by a telescope in 1800. He found that while the colors towards the violet end of the spectrum didn't change the temperature reading on a thermometer a great deal, only about 2 degrees Fahrenheit, as he moved the thermometer towards the red end of the spectrum, the change was greater, eventually reaching about 7 degrees. However, when he put the thermometer beyond the red part of the spectrum, he found an even greater effect of nearly 9 degrees. He thus concluded that the sun produced heat rays, as he called them, a form of light invisible to human eyesight, and he went on to show that these heat rays did obey all of the laws of optics that visible light did, things like the law of reflection and the law of refraction. This, of course, we now know was the first detection and investigation of infrared light. A few years later, the German scientist Johann Wilhelm Ritter would find that beyond the violet end of the spectrum, there were rays that would cause silver chloride to react just as visible light did, thus discovering what we now call ultraviolet light. The second discovery we want to talk about was Thomas Young's demonstration of the phenomena of interference and diffraction with regards to light in his famous double-slit experiment. As these two phenomena were only possible with physical systems that display wave behavior, Young concluded that Huygens had been right all along and that light possessed a wave nature. Shortly thereafter, he used what is known as a diffraction grating, an instrument we'll discuss in some detail in a later episode, to determine the visible light's wavelength to a reasonably high level of accuracy. And he's actually the first guy to do this, and it's very, very important, because what it allows him to do is say light is a wave and that the crests of those waves have a certain spacing or a certain distance apart. He found that red light had the longest wavelengths of the visible part of the spectrum, while violet light had the shortest wavelength, thus showing that the color of light was determined by a physical parameter that was singular in nature. This, of course, meant that the action of a prism to spread out the colors of light, what is known as dispersion, was indeed dependent on wavelength. For typical glass, the shorter the wavelength of light, and conversely, the higher the frequency, the more the light is bent as it passes from air into the prism, and again, when that light is passed from the glass back into the air. By using curved surfaces to form lenses, you can either converge or focus the light to a single point, or you can diverge or disperse the light as if it looks like it's coming from a single point. The third important discovery was made a year later in 1802 by the physician, chemist, and mineralogist William Wollaston. Wollaston had published a paper with the title, quote, "A Method of Examining Refractive and Dispersive Powers by Prismatic Reflection," end quote. It was a somewhat technical work on prisms, but at the end of it he noted, almost in passing, that he had observed the solar spectrum and had found that there were dark lines that seemed to separate the various colors from each other, something that Newton had not reported. He found 5 of these lines that were very dark, which he labeled A through E for easy identification, as well as 2 additional faint lines on either side of his C line that he labeled F and G. He had been successful in an area where Newton had not been, due to his use of a very narrow slit through which the sun's light had been passed, in a method that was otherwise very similar to what Newton had done. Unfortunately, he did not recognize the significance of his discovery, and so it would be left for another to grasp its significance. The final thing we will mention here, more in passing as its relevance won't become understood for more than 100 years, is that in the years between 1801 and 1805, British natural philosopher John Dalton published a series of papers that put forth his atomic theory of matter and the evidence to support it. While it would take another 30 years for the kinks to be worked out of this theory, it would spur enormous growth throughout the 19th century in chemistry and intersect with our story of spectroscopic analysis in the work of Kirchhoff and Bunsen. The next figure we need to discuss is someone whose contributions over his tragically short life would impact the study of light in multiple ways. Joseph Fraunhofer was a Bavarian glass manufacturer whose life reads a bit like a Dickensian rags to riches story. As I hope to do a supplemental episode that looks at the intersection of industrial and scientific practice during the early and mid-19th century in the not too distant future here, I want to include a good bit of biographical information on Fraunhofer in that. So let me be brief on relating the details of his life and leave the rest to that episode. Born in 1787, Fraunhofer was orphaned at the age of 11 and ended up being apprenticed to a harsh trade master in the burgeoning German glassmaking industry. After a few years in the master's service, years that were tremendously hard on Fraunhofer physically, the workshop he was working in collapsed one day, trapping him inside. In a rescue effort, led by none other than the Bavarian Crown Prince Maximilian Joseph, he managed to be pulled from the rubble more or less unscathed, though his physical appearance must have been pretty ragged as the Crown Prince reprimanded the workshop's master and promised to take care of the young apprentice's needs. Fraunhofer took advantage of the opportunity to both further his education and his practical training in the discipline of glassmaking, and was soon hired by another firm where he would spend the rest of his life, rising to the role of not only chief technologist and scientist, but also a partner in the business prior to his death at the young age of 39 in 1826. During his lifetime, Fraunhofer contributed to several advances that must be mentioned. First, he devised a number of ways to improve the process of glass making in Germany that vaulted the products created there ahead of those being produced in England. For those of you who have heard of the extraordinarily lofty reputation of German optics, this is when that begins. Fraunhofer developed ways to create glass lenses of exceptional clarity, lacking bubbles, veins, and warping. Moreover, he developed a machine that could reliably grind his lenses to shapes with much higher precision than could be done by hand. This would make the telescopes he and his firm produced among the most sought after in Europe, with his instruments being used by Struve and Bessel to measure stellar parallax, and in the telescope at the Berlin Observatory that Galle used to first observe Neptune. Now, as part of this endeavor, one of the things Fraunhofer realized was that to build his telescope so that he could achieve the accuracy he wanted, he needed to overcome the chromatic aberration problem. A solution to this had been found by the British optician John Dolland, who had found that by working with a combination of two lenses made out of two different types of glass, he could correct for the differing focal lengths that were imparted to different colors of light caused by refraction of one lens alone. To go into just a bit of detail here, if you will recall, the telescope designs, the refracting telescope designs from Kepler onward, had the objective consisting of a converging lens that was thicker in the middle than it was at the ends, just like you have in a magnifying glass. Due to the fact that the glass acts a bit like a prism, red light is bent less than blue light, and so there's always a problem with the images looking just a bit out of focus. This is that chromatic aberration we were talking about. The thicker the lens, the worse that problem is. Now, it turns out that there were two types of glass commonly produced. They were known as crown glass and flint glass, with the former having a more alkali lime type of compound in the silica, whereas the latter had more lead oxides in the material that was melted. What had been found was that if you made a converging lens out of the crown glass, and then a second lens that was flat on one side and concave on the other from the flint glass, and then you combined them, almost all of the chromatic aberration was eliminated if you got the indexes of refraction of the two lenses just right, which meant you had to get the right mix of whatever those impurities were in the silica that you then melted to form the glass. This is where Fraunhofer's other contribution happens. These lens doublets, as they were called, were extremely hard to get right, in part because there was no real standard by which one could measure the indices of refraction for the glass being produced. So what the Bavarian did was work to develop a standard way to measure this. The way he did this was to make a prism that would take light from an artificial source, in this case a certain type of candle, and break it into a spectrum. He then took a low-power telescope and he used it to examine the spectrum wherein he found that the flame produced a continuous spectrum with the addition of a pair of bright lines in the orange part of that spectrum. Taking these lines as his fixed reference point, he then measured other features in the spectrum with respect to it. This allowed him to calculate how much the prism bent the light and thus determine the index of refraction. What he could then do was adjust the recipe for his glass so that he could tune the index until he got the crown and flint glass indices of refraction in just the right ratio to maximally reduce chromatic aberration. The instrument he developed in 1814 to do this testing was the first designed spectrograph wherein a magnifying instrument, in this case a small theodolite telescope, was used to examine the spectrum produced by a prism. He would soon turn this to the use of examining the sun's spectrum, and what he found was quite remarkable and a huge step forward from Wollaston's work. Due to both his industrial experience with testing and his high-quality optics, what he found was not 7 lines in the spectrum, but over 574 lines of varying width and darkness. What he found was that the lines did not necessarily divide the colors as Wollaston had thought, but were found among them with a given dark line having a color, say green for example, on either side of the line. As Wollaston had done, Fraunhofer labeled the most prominent and or interesting of these lines for future reference, and in time they would come to be named after him. Of particular interest were a set of lines in the violet part of the spectrum that he labeled H, and a pair of lines in the orange region that exactly corresponded with the bright lines produced by the flame he had used for calibration, though he didn't quite know it at the time. That's something that would be discovered later. These lines he labeled D. He also produced a rough measurement of the intensity of the light at each color, with the peak he found occurring in the yellow part of the spectrum. Soon thereafter, he employed Young's method of using a diffraction grating to determine the wavelengths of his labeled lines. In 1823, just 3 years before his death, Fraunhofer extended his investigations to observing spectra of planets and stars with similarly precise results. While the spectra from the planets showed the same characteristics as that of the sun, convincing Fraunhofer that they did shine as a result of reflected sunlight, the spectra of the stars that he observed did show notable differences. It is in this work that stellar spectroscopy begins. And as he was able to assign wavelength measurements to the various features he observed, these sorts of things could be compared by later investigators to see what commonalities and differences they could find. One thing that should be noted here is that at no time did Fraunhofer put forward an explanation for the dark lines of the various spectra he was collecting and documenting. His job was to look at them, record them, and move on. Tragically, Fraunhofer contracted what is known as the White Plague, or tuberculosis, and in 1826, at the age of 13, he passed away. Many of his techniques and glass recipes had been trade secrets, and thus either were not passed along or were transmitted to apprentices only as end products with little or no reasoning to accompany them. Many a scientist would spend a good bit of their intellectual energy attempting to understand and reproduce what the Bavarian had taken to the grave with him. Following this groundbreaking work, progress slowed significantly. Fraunhofer had made a huge jump forward in many regards, but had left a lot of space to be filled in behind him. Slow advances, often hampered by incorrect physical models, would mark the next 30 years. Perhaps the most pernicious idea was that the various colors of light produced by various substances were the result of light waves interfering with other light waves rather than basically being directly associated with some property of the material. While likely drawn from the observation that thin films of substances can produce colored patterns, And in this, maybe the best way to think of this is if you think of a thin film of oil on water and those alternating bands of yellow and blue light one will see reflected from those paired surfaces, which is caused by the physical process of light reflecting off of the lower layer and that interfering with light reflecting off of the upper layer, thus canceling out some colors while amplifying others. This idea that light colors in these spectra were due to the idea of interference would hold back proper spectroscopic analysis of different flames from a number of years. Notable scientists such as John Herschel, William Herschel's son, and David Brewster would struggle to make sense of their results. Herschel would be notable in his suggestion, one echoed by fellow photography pioneer Fox Talbot, that spectra might be useful for chemical analysis. Both men, however, were significantly hampered in their efforts by a lack of truly pure samples to work with. As an example, one avenue of investigation was to produce light from a substance by emitting that light and then shining it through a prism or diffraction grating in order to create a spectrum. What Herschel encountered over and over was that he kept seeing the same pair of bright orange D lines Fraunhofer had observed, regardless of what he used as a source. It turns out that even very small sodium impurities in a substance or a sample will produce those lines, and so Herschel was misled to think that said lines were actually a property of burning rather than specifically being associated with a chemical impurity. It wouldn't be until chemical purification techniques became sufficiently advanced that samples would become available that would resolve these problems. It was also during this period, from the 1820s through the early 1860s, that the chemical technologies associated with photography would be brought together by men such as Daguerre, John Herschel, and Talbot to allow for the more permanent recording of light in a certain way. Herschel was among the first to photograph a spectrum, though his resolution was too low to see the Fraunhofer lines. It would be the Frenchman Edmond Becquerel who would, in 1842, photographically record the first high-quality spectrum, a feat heralded decades later. Just a year after that, this would be repeated by the American John William Draper, whose son will come to feature prominently in a later episode. As part of this move to photographic recording, the sensitivity of the films to ultraviolet light would open up that portion of the spectrum where additional dark lines were noted. It would be Draper who would become the strongest advocate that both heat, or infrared, and chemical, or ultraviolet, rays were, in fact, not separate physical phenomena, but rather the same wave radiation as visible light, with the only difference being the wavelength of the waves. This view embroiled Draper in something of a controversy that had arisen between Brewster and Britain's astronomer royal at the time, George Bidwell Airy. As we mentioned, Brewster strongly advocated the idea that color could be changed by refraction of a light ray through a medium, in spite of Newton's experimental evidence to the contrary, as well as arise from things not associated with the wavelength, in contradiction to Young's evidence. Think again here, this is that idea that light comes about through interference, or that specific wavelengths come about through interference rather than due to the property of the material. So frustrated was he with Brewster's ideas, Airy took Brewster to task in writing, thus prompting a sharp response from the other physicists wherein he accused Airy of being colorblind. It was a bit of an embarrassment for all involved, and it goes to show that scientists, just like all other people, can get themselves worked up in the practice of their discipline. Even as his ideas were being rejected, however, Brewster was providing evidence of the possible origin of Fraunhofer's dark lines. In his observations of the solar spectrum, he noted that some lines became significantly more pronounced when he observed them at sunset. It was known that the path of the light from the sun to an observer would have to traverse a greater thickness of atmosphere due to the more oblique angle at which it came in, thus traveling through more atmosphere. And so Brewster suggested that at least some of the lines in the spectrum came from those wavelengths of light being absorbed by the gases of the Earth's atmosphere. This work built on earlier investigations performed by John Herschel that established that the lines were most likely due to absorption, though Herschel was unclear as to whether that took place at the Sun or on the Earth. Brewster's observations made it clear that some of the lines were in fact due to the Earth's atmosphere. Most of the other investigators we've mentioned in this section were able to reproduce Brewster's results, and so a lively debate also ensued as to the source of the lines, with Brewster and Herschel leaning towards the position that all of the absorption lines were due to terrestrial absorption, whereas others felt that some of the lines were terrestrial and others emanated from within the Sun itself. In 1856, the British Admiralty sent Charles Piazzi Smith to make observations of the solar spectrum from the dormant volcano on Tenerife Island at altitudes between 8,000 and 10,000 feet. In these observations, while he did reproduce some of Brewster's results in the red part of the spectrum, he found many of the other lines completely unaffected by the higher altitude, lending credibility to the position that many, if not most of the lines, were actually produced by absorption at the Sun. The solution to this question, though, would come in the work of one of the most influential figures in 19th century physics. In conjunction with the observations of the solar spectrum, there had been a second research program taking place that worked to analyze the light being produced by various terrestrial sources, mostly flames and electrical arcs. While this work was instrumental in seeding various ideas that would be developed in the 1860s, it was difficult work owing to the problems of setting up an apparatus that would give a clear spectrum, the previously mentioned problem of sample purity, and the struggle to distinguish between two different but related phenomena being most important in this. To understand why this was the case, we need to get just a little bit ahead in our story in order to understand what was happening. When we categorize spectra today, we know that they come in three varieties. Continuous, the rainbow of color we've been discussing, from red on one end to blue or violet on the other. Dark line absorption spectra, as was the case with the Sun, where you have a continuous spectrum with dark lines superimposed on the top of that. And then finally, bright line emission spectra, where you have a limited number of bright lines on a black background spread out across that same spectral distance, if you want to call it that. The first of these is produced by an incandescent solid that has been heated, such as a piece of metal from a furnace or later the filament of a light bulb. The second, as we have been nibbling around the edges of in our narrative here, is produced by light from an incandescent source that then passes through a cooler gas or a cooler material that absorbs some of the light at very specific wavelengths. The third type of spectrum is caused by a diffuse gas that is heated and then emits light at what turned out to be very specific wavelengths. So that's the picture as it would stand at the turn of the 20th century, when the phenomena were clearly characterized, though the causes weren't really well understood. The problem we have at our present point in the narrative, in the period of around 1858 or so, is that experimentation hadn't yet separated out these sort of things, as flame spectroscopy was dealing with the fact that the flames would produce both emission and absorption spectra, and that disentangling those two was proving to be really difficult. Additionally, the instrumentation at this point wasn't great. As an example of this first case, the bright orange lines that Fraunhofer had used in his glass calibration experiments were found in a spectrum that also included absorption lines. These bright lines were part of the flame's emission spectrum, but as the process that gave rise to the observed phenomena had not been understood by Fraunhofer, it was missed that the bright lines were due to the fact that light emitted by trace amounts of sodium in the candle wax had been vaporized in the process of burning, thus producing those emission lines. On the other hand, the absorption lines that he observed came from the envelope of cooler gases that surrounded the flame itself. The first step towards unraveling all of this was taken by the French physicist Léon Foucault, who was able to superimpose the spectrum produced by an electrical carbon arc and the Sun on top of each other in 1849. The carbon, possessing sodium impurities, proceeded to produce the bright orange lines when burned by the electrical arc, and Foucault was able to show that these corresponded exactly with the Fraunhofer D lines in the solar spectrum. Of course, he didn't know that it was sodium that was the cause of the two features, but he did establish that there was a relationship between them. Unfortunately, Foucault's work was largely ignored for almost a decade until it was rediscovered by the man who will be the central part of this last part of our story. Gustav Kirchhoff was born in March of 1824 in Königsberg, Prussia, the son of a well-to-do lawyer. Showing early brilliance, as has been so often the case in our long narrative here, he was put through a rising German education system, earning his undergraduate degree in 1848, after which he moved to Berlin to attend graduate school, and he was soon appointed professor at the University of Breslau. His student work had focused on developing a framework for electrical circuit analysis based on conservation laws, and it resulted in the now famous Kirchhoff circuit laws learned by students of physics and electrical engineering the world over. For our story, though, we will focus on his work while a professor at Heidelberg, where he began to investigate the spectra of various systems. In 1859, he repeated Foucault's experiment and then expanded upon it by passing light from a flame through a large crystal of salt. He found that the salt absorbed the light at exactly the point of the D lines, thus leading him to believe that it was the sodium in the salt that was responsible for the absorption. This led Kirchhoff to develop a theoretical framework that substances that emit strong lines when heated in a diffuse state will also strongly absorb light at the same wavelengths when cooler than the light source itself. Known as Kirchhoff's law of absorption and emission, this would set the stage for an unlocking of a key discovery that would prove Comte's prediction wholly incorrect. Now, before we move on, let's pick up that research track related to flames and sparks. In this track, running parallel to the work on absorption spectra, a number of researchers had been able to produce and examine emission spectra of various materials in some detail, with the most notable of these being the British scientist Charles Wheatstone. In 1835, Wheatstone had shown that various metals could be distinguished by the bright lines created by the sparks that they produced. This gave an alternative method to use instead of the flames when trying to examine emission spectra, and therefore it led to further advances in that field. In 1853, the Swedish physicist Anders Engström extended this to show that emission spectra could be produced by diffuse gases and studied those spectra, specifically the spectra of hydrogen in some detail. Julius Blücher would build on this by identifying specific emission lines in the hydrogen spectrum with the strong absorption lines C and F in the Fraunhofer solar spectrum. All of this set Kirchhoff up to pull together and then vastly expand the dataset. As we noted, by this point in time in his career, he had moved to the University of Heidelberg and had begun working with a colleague in chemistry, Robert Bunsen. And yes, it is that Bunsen, the one of the burner fame. It turns out that Bunsen actually invented the apparatus to do the experiments that would show the things that we're going to talk about just now. Now, Bunsen had a good bit of spectroscopy experience on the flame side to begin a systematic analysis of the spectra of many elements. Due to their combined experience, the two men were able to obtain or synthesize samples of great purity and then produce extremely accurate spectra of them. The key innovation, however, was that Kirchhoff was specifically looking to compare what they found with the spectral lines observed in the solar spectrum. To do this, he used what was the most advanced four-prism spectroscope at the time, allowing him to directly compare the spark and flame spectra that the two men were creating directly with the absorption spectrum of the sun. As a result, Kirchhoff and Bunsen were able to directly identify the presence of iron, calcium, magnesium, sodium, nickel, and chromium in the sun's spectrum, with the identification of iron, for example, being based on matching some 60 emission lines to their absorption counterparts. It is in this that we see Kirchhoff and Bunsen's true breakthrough in terms of what we want to talk about. What is being said in the scientific result here is that each and every element produces a unique set of spectral lines. In the visible part of the spectrum, for example, hydrogen always has 4, and exactly 4 emission lines, and they're always in the same place if the source or the observer isn't moving. Helium has 8 on the other hand, and they're in different spots. Moreover, what Kirchhoff and Bunsen, and to be honest, a number of other researchers at about the same time, are saying here is that the emission and absorption lines for a given element are always found in the same places. This means that it is possible to identify the presence of an element in a sample of unknown material by looking at the spectral lines that the sample produces, either through emission or absorption. There are 2 analogies that tend to work really well here. One is to think of an element's spectrum as its fingerprint. Find the fingerprint, you know the element is there. The other is as sort of a barcode that when read can tell you that you have the presence of the element and, as it turns out, a whole lot more. All of those scenes that you see in your crime procedurals like CSI or NCIS, where they take a mass spectrometer or, more importantly, something like a gas spectrometer or a gas chromatograph or an IR or UV spectrometer, relies on this idea of being able to see different types of spectral lines. Therefore, what Kirchhoff and Bunsen have done is show Comte to be wrong. By looking at the absorption spectrum of the sun and matching the lines found there, Kirchhoff was able to identify the presence of those various elements in what he suspected was a cooler layer of gas in the sun's atmosphere, something we now know to be the chromosphere. They were also able to show which elements in the Earth's atmosphere were responsible for the lines that got stronger or weaker, depending on the time of day the observations were made. It really was a remarkable piece of work that would come to underlie much of both chemistry and astrophysics, as it opened the door to the investigation of the composition of materials that couldn't be tested through chemical reaction, as long as those substances either created or interacted with light. Perhaps the most dramatic application of this can be seen in the discovery of the element helium. In August of 1868, a solar eclipse took place that was visible from the region of what we now think of as India all the way down to the Malay Peninsula. As was common practice at this time, a number of scientific teams traveled to make observations from the path of totality, and among these groups there were a few researchers who sought to observe the spectrum of that portion of the sun's atmosphere immediately above its surface. With the overwhelming glare of the sun blocked by the moon, this was only possible at the time of a solar eclipse, and it was expected that an emission spectrum would result. Among those who would participate in this scientific investigation was the young Lieutenant John Herschel, assigned to work in India, and he of course was the son of John Herschel and the grandson of William Herschel. A scientific dynasty indeed. When observed, the solar prominence did indeed show a series of bright lines, owing mostly to the presence of hydrogen. However, one of the lines, while close to the Fraunhofer D lines created by sodium, it was shifted enough that some believed it to be something different. Among these was Joseph Norman Lockyer, who came to believe that the line indicated the presence of a yet-to-be-discovered element. While he did not immediately name this element in print, waiting to see if it could be discovered terrestrially, Lockyer and his colleague at the Royal Institution, Edward Franklin, began to refer to it as helium, for the name of the Greek god of the sun, Helios. Eventually, in 1881, helium was first observed by the Italian physicist Luigi Palmieri, and then isolated in 1895 by William Ramsay. As we wrap up this episode, there are a few matters of ancillary interest we need to spend just a little bit of time on. The first has to do with something common to all things that exhibit wave behavior, and it's known as the Doppler Effect. Derived by the Austrian physicist Christian Doppler in 1842, it says that the frequency and conversely the wavelength, of a wave will be perceived by an observer differently if either the source of the wave or the observer, or both, are moving either towards or away from each other. In sound wave, this means that the observed pitch, that perceived sort of attribute that depends on the wavelength, will increase if the source and observer are moving towards each other and decrease when moving away. An effect anyone who has either seen any number of British detective mysteries or has had to wait for a train locomotive to pass by a crossing has likely observed. In the case of light, this Doppler effect results in a shifting of the entire spectrum towards the blue end of the spectrum if the relative velocity is towards the observer, and the shift is towards the red end of the spectrum if the velocity is away. This will become very important a ways down the road. The second thing we need to mention is that during this time, there are a number of advances being made in the fields of electricity and magnetism that eventually result in showing that these are related phenomena. Building on the work of Gauss, Ampere, and Faraday, James Clerk Maxwell will show that light is a wave in the electromagnetic field, and that color indeed is a physiological thing tied to the wavelength of the electromagnetic radiation. He will show that there is a spectrum associated with this physical phenomenon, and that both infrared and ultraviolet light are manifestations of this outside of the realm of human vision. In time, this spectrum will be expanded to include things like radio waves, X-rays, gamma rays, and of course, cosmic rays. His unification of the separate phenomena of electricity and magnetism in the mid-1860s will also set the stage for the work 40 years later of a young Swiss patent clerk that we seem to keep mentioning. Finally, as we've already noted, it's during this period that photography will be developed. This, of course, will eventually allow for the capturing of detailed spectra, as we've already mentioned, in a permanent way that will allow for measurement and comparison, something that will prove to be vital to the development of stellar spectroscopy. So, as we close, let me make just a couple of administrative remarks. That's at least what I call them in my class when I teach that. As always, thanks for taking the time to listen to the show and for being a part of the crew. On a recent bike ride, I was reflecting on just how amazing it is that you give up parts of your life to consider my ramblings. I hope that you find it worth your while, and that I've gotten you to both understand and appreciate just a bit of how we arrived at some of what we know. This is one of those topics that can be a bit tricky, and so, of course, as always, we'll post diagrams on our website at thescientificodyssey, all one word, .typepad.com. If you'd like, you can also go back and listen to our episode in our History of the Atom series, where we look at this same topic from a more chemistry-focused perspective. The relevant episode is 2.13, the quantum atom. I'd like to give a shout out this week to our listeners in the Kansas City area. Thanks so much for tuning in, and if you're so inclined, post a photo of yourselves to the Odyssey's Facebook page to say hi to everyone else. For all the students out there, I hope your finals have gone well, or if, like us here in central Kansas, you got off to a bit of a later start this year and are still in the middle of your finals, I hope you're in a great place and you're handling them well. For the high school and younger students, you're in the closing stretch. Finish strong. For everyone else, if you've got a moment, why not do something this week to spread the word about the show? Maybe share a link with a friend, coworker, or classmate that you think might really enjoy what we're doing and talking about here. Another way to reach out would be for you to post something about the show, maybe a link to this particular episode or whatever, to whatever social media feeds you happen to use. Let folks on Facebook or Twitter or Instagram or wherever know that we exist, and encourage them to come check us out. Another thing you can do is, of course, leave a review. Let's see what we can do to get the word out. One of the crew sent me a note to tell me that he feels the show is, quote, one of the greatest and most underrated shows on the internet, end quote. I really appreciate that sentiment, and I'm really humbled by that feedback, and it really does inspire me to do everything I can to let more people know what we're doing on our voyages of discovery. Won't you help me grow the crew just a little bit? Finally, thanks to the Blue Dot Sessions for the use of their music. You can find out more on their recently redesigned website, www.sessions.blue. Next week, we'll take this new knowledge about light and spectra and see how it can be applied to the study of stars in the vast reaches of space. Until then, full sails on your journey.